Well, hi there. We're going to have a look at properties of mean and variance of a continuous random variable in this session. So let's get going. Properties of the mean. Now, guys, as with the discrete random variables, we can say that in general, the expected value of some function of x, where x is a continuous random variable, is not equal to the function of the expected value of x. Yes, I know. Just reflect on that for a moment and you'll get it when I show you this, which is about to follow. Where g of x is a non-linear function, that's important, non-linear function of x. So e of g of x, generally speaking, does not equal g of e of x. Now, if, for example, g of x was x squared, we'd be able to say that the expected value of x squared is not equal to the expected value of x all squared, where this thing here, the expected value of x squared, is the expected value of g of x, and this expected value of x all squared is g of the expected value of x. Okay, so they're not the same thing. But if you have a linear function of x, for example, if g of x was ax plus b, then they are the same thing. We know that as for discrete random variables, we know that then e of g of x does equal g of e of x. In other words, the expected value of the linear function is equal to the function of the expected value. Okay, that's what it means. Does that do in your head in? Well, don't worry about it. Just remember the formula. It works. So we're saying that the mean of the linear function is equal to the linear function of the mean. Good heavens above. So that's what it is. Okay, and we did use that rule in the discrete random variables as well. It's exactly the same rule. I'm going to prove it for you. It's pretty easy to prove actually, but you won't have to know how to prove it, so don't worry about that. Alright, so if we prove it like this, we say, okay, the expected value of, say, ax plus b, a linear function of x, would be the thing itself, the function times f of, the integral of the function itself times f of x with respect to x from minus infinity to plus infinity. And if you split those two terms in the integral, which have the plus sign between them, you get the integral of a times f of x with respect to x from minus infinity to plus b times this thing here. Yeah, you agree with that from the previous line? Okay, now that's very, very good, because first of all, you can take this a outside the integral sign because you don't integrate constants, and you get this. My goodness, what is that? Well, that thing there with the, if you take the a out here, what's left here, the integral expression is just e of x, the expected value of x, because it's x times f of x integrated with respect to x from minus infinity to plus infinity. And this beastie over here is just b, because what's behind the integral sign here, guys, is just 1. So there, look, we proved it. Very easy to prove. But what I want you to do is remember this equation here in case you need it. I don't think it really comes up very often at all, but just remember it, put it on your formula sheet or something and take it into any exams with you just in case you need it. Now, variance is again the same equation we came up with for the discrete random variable. Okay, so if we consider the variance of a linear function of x, such as the variance of ax plus b, I'm going to prove this for you. Again, you won't have to prove it, so just fasten your seat belts and watch this. I like to prove things because I like to know where they came from, but you won't have to do this, so just view this with interest rather than the need to reproduce it. So the variance of ax plus b equals, now according to our variance formula, it's the expected value of the thing squared minus the expected value of the thing all squared. Okay, you get that, don't you? We've been doing that for yonks now. Okay, same old, except I've just got this ax plus b in here instead of just x, is what you're more used to seeing. Okay, now what I'm going to do now is take this first term and analyse that a bit, and then secondly I'll be taking this second term and analyse it a bit, and then we'll take this one from that one after we've fiddled with them for a bit, and you'll see the result is very satisfying. Now, okay, this term here. Alright, so let's have a look at that. that is the expected value of this quadratic thing multiplied out, which, as we know, that would come out to be the expected value of this thing plus the expected value of this thing plus the expected value of this thing. Okay? Yes, and I've taken the a squared from the first term out the front, and the 2ab from the second term out the front of the, the ex term here. And the last thing is e of expected value of b squared, which is just going to be b squared because that's a constant. So, where does that get us, guys? That gets us a squared times the expected value of x squared plus 2ab times, I'll call that mu, expected value of x, plus b squared. Alright, that's so far so good. Now let's take the second term up here like I said we were going to do, and we'll fiddle with that now. So the first thing I did was I said, okay, this thing equals a times the expected value of x plus b all squared instead of the expected value of ax plus b. You know from the previous screen we're allowed to do that. Now we're going to multiply this beastie out I've just called it a times mu. Okay, where expected value of x is mu, just to do a little bit of shorthand here, plus b all squared, multiplying it out. Okay, what's that? Does it look right? I think so. Yes, it does. Good. So therefore, the variance of ax plus b is equal to this thing minus this thing, because it's the same as that thing minus that thing. Okay. Now, you can see, because of this minus sign here, that there's some cancelling going to happen. This is going to cancel with this. This is going to cancel with this. So have a look. Yeah, those ones cancel. These ones cancel, and we get yes. Do we? Yes. I've just morphed back into instead of saying a squared mu squared here for this term here, I've morphed back into expected value of x instead of mu, because it allows us to see more clearly in the way that we're used to what this thing inside the brackets really is. It's actually the variance of x. Okay, so we're getting a squared times the variance of x. So that is our result. So the variance of a linear function of x, ax plus b, is just a squared times the variance of x. Now, if you actually reflect on that, guys, it makes perfect sense, because if you think about this, I'm going to, if I take this linear function of x, okay, I'm dilating it by a factor of a, multiplying it, scaling it, dilating it by a factor of a, and then I'm going to move it b spots to the right in an x sense, alright? Now, variance is about spread, okay, measures of spread. So if you just simply displace a whole function, if you like, a probability density function, b units to the right, you're not going to alter its spread characteristics at all. So this b term here would not be expected to impact the variance of x at all, okay? But the a term certainly would, because if you dilate something by a, you just imagine, say, a bell curve, for example, where you know where the mean is the middle, the hump, the top of the curve, yes, where the x value is corresponding to the hump of the curve. Now, do you imagine the spread either side of that mean point? If you dilate that whole curve by a factor of a, in other words, you spread it out, okay, multiply everything by a, then everything that was already spread either side of the mean will now be spread a times more than what it was before, and therefore you would certainly expect that the spread would be increased by a factor of a, and because variance is the square of the standard deviation, where standard deviation is the average deviation from the mean, you would expect an a squared term here for the effect of this on the variance. Yeah, that's my analysis of it anyway. I think it's pretty right. Yeah, so that makes sense. All right. Now this is the second part of the presentation today, and it's really pretty important. So I want you to pay close attention, if you wouldn't mind, because if you don't, it can come back and bite you. Now, okay, linear transformation of a continuous random variable and its PDF. What a grouping title. However, it is important. It is important. So come on, let's go and have a close look at it. If a continuous random variable x is transformed into ax plus b, a linear function and a linear transformation, then this represents transformations of the following if we analyse them. Firstly, you've got a dilation of a factor of A from the y-axis or in the x direction. You know that. That's what that does. Multiplies everything by A away from the y-axis. And secondly, we've got a translation of B units in the positive x direction, that is to the right. Okay, now that's what we're doing to Mr. X here, right? That's what this does to Mr. X, yes? Now, we also know that if you've got a probability density function, if you go morphing all the x values over to ax plus b, then the poor old y values that belonged to those original x values on the PDF, right, they will similarly have to be tootling over to the right so that they basically match up with the original x values which they belong to before the x values got translated by this thing up here, right? So in other words, these x values had y values belonging to them. Now these x values are morphing over to the ax plus b position. The y values must go with them. Okay? The y values must go with them and match up with them again. Therefore, the PDF itself gets transformed. Now, what we're going to do is we're going to try and work out what the new transformed PDF is. So if we had an original PDF y equals f of x, if x is transformed to ax plus b, then what is the transformed PDF? That's our goal, okay? And it's back to Transformation City, okay? So, yes, it is important, even though it's a bit unpleasant, okay? Now, if I represent the original PDF by this little graph here, a nice little symmetrical triangular one, with an area of 1, the mean is at x1 in this diagram, right? And the area is 1. Because if it's not 1, we haven't got a PDF, guys, we've got an imposter. Now, we're going to transform that PDF as follows. Oh my goodness, look at this. Well, it certainly has been stretched, hasn't it? That's sort of all stretched out, yeah? Much wider sweep from one extremity to the other in terms of x than what this one's got, yeah? And secondly, you notice that the mean, which was at x1 here, it's now moved to a times x1 plus b. And you'll notice this little bit over here is b to signify that this whole thing is stepped along, because this point here, which was at the origin, has now moved b units along. And of course the area is 1. The area is 1 again, which we're going to talk about in a minute. It's very, very interesting. You might notice that this function looks, its apex is not as high a point in terms of the y as what this one is, and there's a very, very good reason for that. So just note that fact, and we'll talk about it as we go along, okay? Now, alright, in the x direction, we know that the transformed values of x dashed, are a times the original value of x plus b, alright? Now, if you make x the subject, just rearrange this equation here, you'll get x is 1 over a times x dash minus b. If you care to check that out, I think you'll find that's right. Now, that is the transformed value of x. This is re-expressing it in terms of the original value of x in terms of the transformed value, which you'll see why I want to do that in a moment, alright? Now, in terms of the y direction, look, there's no y transformation in and of itself, because all we did here was we moved the x thing over here in terms of the ax plus b transformation, but we were not called on to do a y transformation as such, were we? So x and y would go to ax plus b and y, which I'll call x dash and y dash, yes? However, guys, there is a complication. There is a complication, and we do need to do a y dilation. It becomes necessary for another reason, and I'll explain that now. In the x direction, guys, the graph of the PDF has been stretched or dilated by a factor of a. It has, hasn't it? Yes, it has. So therefore, we've got a big problem here. This means that the area of the transformed PDF, quote unquote, is no longer 1. In fact, the area will be a. It will be a, because we've stretched the linear dimension in the x direction by a factor of a. Okay, So we haven't got a PDF anymore, guys. We've got something which is a bit sick if it really wants to be a PDF. So what we do, we have a little strategy, an ingenious strategy to fix this problem. We have to have the area under a PDF equal to 1, otherwise it's no PDF anymore. So what we do, because we've just stretched the x dimension by a factor of a, we shrink the graph by a factor of a in the y direction to compensate. We squash it, push it down, and shrink it by a factor of a, thereby preserving overall the area of the transformed PDF as having an area equal to 1. That's what we do, and that's why the height of that little transformed graph on the previous screen was less than the height of the original untransformed one. That's why, because you have to squash it by a factor of a in the y direction to compensate for the fact that there was a stretch in the x direction so that the overall area is still 1. So therefore, guys, we dilate the PDF by a factor of 1 over a. That's the way you say it, right? You don't say squash or compress. You say dilate the PDF by a factor of 1 over a from the x-axis, or that is in the y direction, to preserve the area of the transformed PDF so that it has a value of 1. Now we're back in business again, all right? So let's go with this, what we were saying before. We know that x got transformed to ax plus b. Now we know that y has to be transformed of necessity to y over a. In other words, it's compressed, it's squashed by a factor of a. All right? Okay, so this is what we're saying now. So therefore, this is my transformed x, which I'm going to call x dashed. This is my transformed y, which I'm going to call y dashed. Yes. All right. Now, just making that very, very clear, x dashed is ax plus b, and we know that y dashed is y over a, and that's the key to everything, as I call it, the key to absolutely everything in transformations. Yes? Now, what I'm going to do now, guys, is I'm going to rearrange this to make x the subject, rearrange this to make y the subject, and then I'm going to substitute those values as follows. There's x. Have a look, see if you agree. Yes. There's y. That's right, isn't it? Now, the original y equals f of x, PDF, right? I'm going to re-express that little equation there by substituting y as ay dashed and f of x, where the x is going to be x dash minus b all over a. Okay, so I'm substituting this in terms of the transformed equivalent beasties. Okay, and what it becomes is ay dashed as y equals f of x dash minus b over a as x. Now that, guys and gals, is the new morphed transformed PDF. Da-da-da-da. I'm just going to print it up a bit. I'm dividing both sides by a just to get y dash, to solve for y dash. That is it. Now, it's a little, it's now morphed in from the caterpillar into the butterfly, and there it is. Now I'm going to drop the dashes, and that's going to be, you ready for the unveiling? There. Okay, y is 1 over a f of x minus b all over a. Okay, and incidentally, if you're good at reading off the transformed functions, knowing that the original was the base model function, that is y equals f of x, if you're good at reading these off in the d and then r and then t, that is dilation, reflection, translation sequence, you would know that this a is a dilation of a factor of a in the x direction or from the y-axis. That's the d. Then there's no r. Then there's a t here for the x, which is a translation of b units to the right, which tallies with what we said. And thirdly, this one here, this is a y dilation of a factor of 1 over a from the x-axis or in the y direction, or in other words, a squashing of a factor of a down, okay, which is exactly what we've just been saying, okay. So that's our new transformed probability density function when x is changed from x into ax plus b. Yes? Woohoo! Okay, example 1. Let's go. X is a continuous random variable with a mean of 10 and a variance of 4. Find the expected value of this linear function of x and find the variance of this linear function of x. No problem, guys. We just use those formulas, plug and chug. This third one is where I'm going to dwell a bit. If x has a probability density function with the rule f of x, describe the rule for the transformed PDF g of x in terms of f of x for both of these situations, that one from A and that one from B. All right, let's go for it. There's A today, hooray. What do we got? Yes. Oh, yes, that's the thing, isn't it? That's the thing. That's the formula we came up with before. So the expected value of 3x plus 1 is just 3 times the expected value of x plus 1. We know the expected value of x was, what was it? 10. Okay, so just plug and chug. 3 times 10 plus 1 is 31. That's it, guys. I mean, that's as easy as anything, isn't it? Yeah? So the second one, B. Now, the variance of that, okay, well, we know that the coefficient of the x term is -4. So that's like the A term. The 1 is like the B term. So we know that the variance of that is going to be a squared times the variance of x. Now, if a is -4, -4 squared is 16. And 16 times the variance of x, which was 4. 16 times 4 is 64. And that's your answer. So that stuff is really, really easy. C is not so easy, so let's do it. C1, that is for x morphing into 3x plus 1. Okay, it's the same procedure as I did on the previous screen, so let's do it for just a bit more reinforcement and practice, yes? So we can say, guys, that any point x and y on the original PDF gets morphed into 3x plus 1 in terms of the x, but the y, we have this compensating factor of a factor of 3 to squash the y down to make up for the fact that the x has been stretched by 3. Okay, horizontally stretched by 3 and vertically compressed by 3 to make sure the PDF area is still 1. Alright, now that's x dashed and y dashed. Now we just go through the same routine, guys. Therefore, x dashed is 3x plus 1, y dashed is y over 3. That's the key to everything. Yes? Good. Now we're going to make x and y the subject and plug and chug into the original y equals f of x formula as we did on the previous screen. So x is that, isn't it? Oh, yes. And y is that. Yes, very good. Now, okay, so y equals f of x becomes, right, now the y is, in terms of the transformed beastie, this thing, and the f of x is such that the x is this funny looking thing, right? So we can say, therefore, we've got y, what am I going to do? Oh yeah, that's it there, right? 3y equals that thing. Yes, and therefore just dividing both sides by 3 we get that, and therefore that's our new transformed function, which we're just going to pretty up and call g of x, because that's what they wanted us to call it, g of x, yeah? So drop the dashes and call it g of x, and we get that. Yeah, that's it, Alright, you happy? That's how you do them, and look, you need to practice this to get good at it, because it's just transformations all over again, and it's really good revision of that stuff, because it's a while since we did it. And it's all over the place in the normal distribution, which is coming up as our example distribution of a continuous random variable distribution in the next lot of videos. Okay, now we'll do C part 2. Now that's this one here. Okay, we're looking for the transformed PDF when x is morphed into 1 minus 4x. Okay, so if x goes into minus 4x plus 1, which is just another way of saying it, we can say same old, x and y on the original PDF goes into minus 4x plus 1, and then y over 4 as a compensating squashing effect in the y to make sure the area is preserved in the transformed PDF as having an area of 1. Alright, now that's x dash y dashed. Okay, so therefore x dashed is minus 4x plus 1, y dashed is y over 4, and that's the key to everything. Now let's make x and y the subject as we're getting used to doing. Does that look right? Yes, it does. And y is that. Now we're just going to substitute for x and for y into our y equals f of x equation as this. Looks like a bit of a mess, doesn't it? But still, that's all right. That's the y, and it's f of x, which x is there. These are the transformed variables, all right? Now, all we need to do now, guys, is solve it for y dashed by dividing both sides by 4, then dropping the dashes and calling y dashed g of x. And there it is, and thank you, Mr. Box, and there's the answer. Okay, now, look, me doing it is okay, but you doing it is practicing it and making sure you really can do it, guys. So do yourself a favour, do it again, you know, without me showing you, okay? Here's another example with a real life PDF this time. So let's have a look. We're saying that the continuous random variable x has a probability distribution as follows. F of x equals 3x squared over 2, where x goes from -1 to +1, inclusive, and it's 0 at all other spots of x, yes? Now, what we're required to do is to find the probability density function for 3x minus 2. So x is being morphed into 3x minus 2. What does that do to this PDF? Okay, what does it do to it? So it's the same procedure, guys. It's just that we're substituting a real life value of a PDF here. I checked that this has an area of 1, and it does. So everything's good there. Alright, now, taking any point on the original PDF x and y, okay, the transformation required is if x goes from x to 3x minus 2 will be any point on the PDF x and y goes to 3x minus 2 and y over 3, squashing it down by a factor of 3 in the y to compensate, as I've been explaining ad nauseam. And that's x dashed and y dashed. Okay, here comes the old summary. Therefore, x dashed is 3x minus 2, of course, and y dashed is y over 3. That's the key to everything. Now we make x and y the subject. Yes, there's x. Do you agree? Yes, good. And there's y, and yes, you agree with that. Now we just substitute. Now this is a little bit more complicated, substituting it into a real life thingy. So let's do it. We know that y equals f of x equals this thing. Now we're going to substitute y in terms of the transformed thingy, y thingy, and we're going to put x. Everywhere we see an x, we're going to put this beast here, right? There. So that's going to go there. It's going to go there. And it's going to go, wait a minute. Yeah, that's right. And it's going to go there, and it's going to go there. Okay? Now, let's go. Right, so we're saying that will become after substituting, as I've been explaining, for x and for y. It's going to be very messy, but we'll just persist and we'll get there in the end, guys. So, okay, so y becomes 3y dashed, as I was explaining up here. That's going to be f of all of this mess. Instead of x, it's going to become this thing, right? That's going to be 3 over 2, the messy x thingy, transformed x thingy squared, where, look at this mess. Look, we've got 1/3 of x dashed plus 2 is going from -1 to +1 inclusive, and down here we've got the thing equals 0, the PDF equals 0, where we've got it used to be x was less than -1 or x was greater than 1. This time it's this thing is less than -1, or this thing is greater than 1. So now, I know, look, just one step at a time, everything will be good. So don't lose it now, guys. We've got it together. Now, okay, solving for y dash, we've got to divide both sides by 3, okay? That's that step there. Now, alright, so I've simplified it a bit there as well for you. Actually, I've simplified the whole thing because it was getting so messy. If you just work all that through, if you square this whole thing and multiply it by that, remembering that you've got to divide by 3 as well, you'll get this thing here morphs into that, right? And this thingy here, if you work that out, this expression here gets you to there. X dashed will be greater than or equal to -5, less than or equal to +1. And over here we've got the PDF equals 0 for x is less than -5 or greater than 1. My goodness. And so therefore, if the PDF was g of x, then g of x would equal that. I've dropped the dashes and I've just made it look a bit prettier now. Okay, that's it. All right, that's your answer, and that is it. And you're a star, huzzah! You'll go far, but you will need to practice this and get really good at it. And that was a very important area that we've just covered there. Okay, it could come up in an assessment situation because it involves transformations, and as we know, students do find that very hard. So you need to get good at it, guys. Thank you for coming to see me, and all the very best to you, and we'll see you soon.